Hi everyone, myself Dr. E. Sridevi, Professor, Department of Electronics and Communication Engineering. In this video, we are going to study about magnetic field intensity due to the axis of circular loop. So on completion of this module, the learners can able to understand the magnetic field intensity on the axis of circular loop. First, we are going to calculate what is H on the axis of circular loop. For that, let us assume that loop carries a straight current I and the point of observation P is the point where we are going to calculate H. So this P lies on the Z axis at the distance Z from the plane of loop. Now magnetic field H on the axis of circular loop in xy plane is given as like this. Consider this diagram here. P is the point where we are going to measure and x, y, z are the axis, and here the current carrying element is I. So considering this loop carrying direct current I placed at xy plane within the z axis, now according to cylindrical coordinate system, dl equal to dr into ar plus r d phi a phi plus dz az. The circular loop lies on the xy plane. The radius of the loop is r. The point P is along the z axis. The differential element of length on the loop is dl. But dl is the plane for which r is constant and z is equal to 0 for constant plane. The ideal is tangential at the point 1 and a phi direction. So ideal equal to ir d phi d a phi. So r12 equal to modulus vector r12 divided by modulus r12. So substituting and finding this value of r12 equal to square root of r square plus z square. Here r is the radius of loop, which is noted as a constant, and phi is the azimuth angle. Z is the distance along the axis. The current element ar12 equal to minus rar plus az plus r square plus z square. Substituting these values in the vector expression, dl cross r12 is equal to, so substituting all this in vector product, it will be vector matrix z into r d phi ar plus r square d phi az. According to Biot-Savart law, the differential field strength dH at the point P is given by dH is equal to IDL into AR12 divided by 4 pi r square. Here R12 is neglected while obtaining the cross product. The total H is to be the point obtained by integrating phi from 0 to 2H. So H is equal to, substituting here it will be 0 to 2 pi Z R d phi divided by r square plus z square the whole power 3 by 2 into cos phi ax plus sin phi ay. The unit vector ar is expressed in rectangular coordinate system as cos phi ax plus sin phi ay. Now 0 to 2 pi cos phi a phi cos phi d phi is equal to integrating, it will be sin phi limits starting from 0 to 2 pi. Substituting and from the limit 0 to 2 pi, the value is equal to 2, and it will be H is equal to I r square a z divided by 2 into r square plus z square the whole power 3 by 2. Here r is the radius of the circular loop and z is the distance of point P along the axis. The magnetic field intensity at the center of circular loop is also calculated like this. P is the point where we are going to calculate the H. Point 1 and point 2 are noted, and ideal is the current element and conductor in the free space, and I is the current carrying wire. Magnetic field intensity at the circular loop is calculated by substituting Z is equal to 0 in the above equation. Substituting H is equal to I into r square into AZ divided by 2 r cube, I AZ divided by 2 r ampere per meter. The direction of H is along Z axis. So first integral term equals 0 due to radial symmetric. Magnetic field depends on current I, radius r and distance Z, follows the Biot-Savart law. So here the this one is the Z is the magnetic, H is the magnetic field intensity due to circular loop carrying current. So here H is equal to I into AZ divided by 2R ampere per meter. So hope you all understand this session. Thank you for listening. Thank you.